Hello students, in this session we are going to study polar moment of inertia. Although there are many shafts, rectangular shaft and square shafts, but we will be discussing here only about the circular shafts. And what is torsion? Whenever apply a torque, a force multiplied by the distance is the torque. So whenever we apply a torque to a shaft, the stresses will be developed due to the material of the shaft, and that stresses are the shear stresses, and that twisting of the shaft is called torsion of the circular shaft, right? So suppose this is a circular shaft and we have given a twist by using a torque. We have applied a torque to this shaft, and as the body is in static equilibrium, like in the case of bars, remember the bars, we have a analogous case with the bars. We will compare always with a bar. Torque and bar are similar to this in calculations, but there it is a torque and here it is a force, right? Suppose we have applied a force to it, and this body is in static equilibrium because it is fixed at this point. There will be a reaction, similar reaction, which is equal to P, developed at this rigid support. Similarly here, because the body is in static equilibrium, so there will be a resisting torque developed, reaction of the torque developed at this point, right? And this T must be equal to TR. This T must be equal to TR because the body is in static equilibrium. So this is the torque. This is called torsion of the circular shafts, and there will be a twist. There will be a twist in the shaft like this. Suppose we are making a circular shaft. This is the area of cross section of the shaft, and if we see from this side, there is a twist, angle of twist of this shaft. Suppose this is an angle of twist, theta. So theta is called the angle of twist due to this load applied. So torque is analogous to the load applied. The torque is analogous to the load applied in simple stresses. So I am writing here, torque is analogous to load applied in simple stresses. This is the angle of twist due to the torque, and there is some elongation or deformation in this bar due to this load applied, like in simple stresses. The length of the bar is L, and also the length of this shaft is L. So same length, same shaft, when a tensile load is applied, direct load is applied, there is deformation. So this angle of twist is analogous to this elongation in the bar. Here delta is the elongation in the bar. So both are analogous. So theta is analogous to delta L, right? There is quite similarity in calculation, and your calculation will become very easy if you compare this case with this case, right? Most of the calculations are very analogous, right? So torque is analogous to force applied, angle of twist is analogous to this, and there will be some stresses developed in the material. Stresses developed in the material like this. Suppose this is a tensile stresses developed in the material, and this is sigma. Similar to this, there will be shear stresses developed in the material. Shear stresses developed in the material, right? And shear stresses, if we show shear stresses like this, suppose this is a shear stress, so we have to show on the parallel tangentially, right? You know that the shear stresses are really shown on parallel to a point, right? Tangential to the point, right? So the shear stresses are developed. Shear stresses are developed in the material. So you can say on this axis, the shear stresses will be developed like this, right? Shear stresses will be developed, right? Although this is uniform on the cross section, it is not uniform. We will study it later on. So this is the shear stresses developed in the material. So due to torque, shear stresses are developed. We will find out later on. And due to force, direct force, tensile stresses are developed in this material, right? So Some analogous we will use for ease of calculations, right? So, and why these stresses are developed in the material? Why stresses are developed in the material? Because the body of the material is resisting this twist, right? Resisting this twist. Like this here, the body is material is resisting the deformation. Similarly, there is a resistance offered by the material to this twist. So there is a very important term used in torsion of circular shafts. What is that? So an important term used in torsion of circular shafts, that is, or whatever shafts is there, that is called polar moment of inertia. Polar moment of inertia. As you already studied moment of inertia in your basics, that moment of inertia is a quantity which is a resistance against rotation. If a body is going to rotate or revolve, a term comes like moment of inertia. So it is similar to the mass. A material, if I push a material, the mass of the material, it will offer inertia, resistance. That mass is in simple loading, right? But when we are going to rotate a body or area, it may be a mass or it may be area, it is going to offer a resistance, that is called moment of inertia. But when we are going to, but there are three axes, x-axis and y-axis. There is another axis, z-axis. So if we are going to rotate a body about central axis, z-axis, there is another term came, that is called polar moment of inertia. So suppose for the time being I am making a rectangular shaft for more clarity. So suppose there is a rectangular shaft like this, and it will be applicable to circular shafts also, but to define this polar moment of inertia I am using a generalized case of rectangular shaft. This is a rectangular shaft. Suppose this is a rectangular shaft, right? So we have here three axes you can see here. One is this is our rectangle. This is our rectangle. Suppose A, B, C and D, and there is one axis in this direction, suppose x direction, one axis in y direction perpendicular to this y direction, this is x, this is y. There is one more axis, this axis, this is the axis of the shaft, this is axis of the shaft, central axis of the shaft, like this, right? This point is passing through this point, like this, here, this, and this one more axis is there, that is called z-axis, right? Z-axis. And polar moment of inertia come into picture when we try to twist this body about z-axis, this central axis, like center of the shaft, right? About z-axis, then a moment of inertia is the resistance, that is the material property, the resistance offered by this material against the twist, right? So what is polar moment of inertia? Basically it is the resistance against torsion or twist offered by the shaft, right? So this is the resistance offered by the shaft, that is called polar moment of inertia. This is similar to the simple moment of inertia when a body is rotating. So there is it offers a resistance. Now the body is going to twist about z-axis, then the pictures one more moment of inertia comes into picture, that is called polar moment of inertia. So how mathematically we find the polar moment of inertia? We already know the moment of inertia, we have already done. What is polar moment of inertia? So if I make this rectangle here, I want to make rectangle here, I am making somewhat bigger one. This is same, but I am making somewhat bigger one for more clarity. This is A, B, C, D, A, B, C, D. This is our x-axis, right? And this is the y-axis. And third is the z-axis, right? Third is our z axis, right? And this is origin. So what is polar moment of inertia basically, right? So now let us take a small element. Let us take a small element, because this body is going to rotate, and we have to going to twist this body about z axis. So about z axis, suppose this is the material at a distance r from this center position. So let us say there is a small element we have taken. Suppose this is a small element. This small element we have taken at a distance r from center, and this is at a distance of x from the center in x direction, and at a distance of y from the center in y direction. So this is y distance, this is x distance, right? And this is our small element, right? So ds or dA, right? So this is small area dA we have taken, which is at a distance r from the center. In x direction it is at a distance of x, in y direction it is at a distance of y from the origin, right? And by definition, polar moment of inertia of this element will be defined as, polar moment of inertia of this element is defined as, that is equal to r square dA, and if we integrate it, we will get the total polar moment of inertia of this entire section, right? So that will be equal to an integration of r square dA. So this is how the polar moment of inertia is defined. Polar moment of inertia is defined, right? And what is r square in this triangle? In this triangle, what is r square? You can see here what is r, that is equal to under root x square plus y square, x square plus y square. You can see here x square plus y square. So put here, you will get j. This is the symbol for polar moment of inertia is j. You can use j, or sometimes people use the symbol IP. I is the moment of inertia and P means polar moment of inertia. So you can use any symbol for this. We are using J for this, right? So J will be equal to, what is R square? This is x square plus y square. So this is integration of x square plus y square dA, and J will be equal to integration of x square dA plus y square dA. And what is x square dA integration? This is the moment of inertia about x-axis, Ix, and this is the moment of inertia about y-axis, Iy. So J is basically Ixx plus Iyy, right? So this is our polar moment of inertia. You must know that this is also called perpendicular axis theorem. This is also called perpendicular axis theorem of moment of inertia, right? Perpendicular axis theorem, you should remind that, right? So polar moment of inertia is a moment of inertia in x direction plus moment of inertia in y direction. So in x direction we have some moment of inertia, x direction. In y direction we have some moment of inertia, and in perpendicular direction, perpendicular to x and y, to this plane, perpendicular to this plane, this is our z direction. So in z direction, the moment of inertia is given by Ixx plus Iyy. So this is the polar moment of inertia, right? Now let us find out polar moment of inertia of a circular shaft. So what will be the polar moment of inertia of a circular shaft? We have used a generalized case. Generalized case was there that polar moment of inertia is given by integration of r square dA, which was come out to be Ixx plus Iyy, right? This we have already studied. Ixx plus Iyy. So this is J is equal to r square dA by definition, and by derivation it come out to be Ixx plus Iyy, where x and y are in same plane and z is the perpendicular plane, right? This is the polar moment of inertia about the perpendicular plane or z plane, right? Z axis, right? So if J is equal to Ixx plus Iyy, Ixx plus Iyy, so a circular shaft, suppose we have a circular shaft like this, circular shaft like this, and it has a circle, right? And this is the z axis about which we have to find the polar moment of inertia. This is z, and there are two planes here. From watching from this side, this is x, and this is y, right? And we want to find out the polar moment of inertia about this axis, right? So Ixx plus Iyy, and suppose it has some dia d, suppose it has some dia given d is the dia of this shaft. Then what is Ixx? Why Ixx? You must remember that the moment of inertia of a circular shaft is given by, you must remember that, pi by 64 d to the power 4, right? About any plane passing through this circle, right? So moment of inertia of this circle about a plane, about an axis in the same plane xx, right? So that is pi by 64 d to the power 4. Similarly, what will be Iyy? Because of uniformity, the same moment of inertia will be there in this direction, pi by 64 d to the power 4. And when we combine it, we will get the polar moment of inertia about this axis, perpendicular axis, right? Perpendicular to this x and y, right? So that is J polar moment of inertia, or Iz. You can say Izz, right? So that will be pi by 64 d to the power 4 plus pi by 64 d to the power 4. Solve it and you will get pi by 32 d to the power 4. After solving, you will get the equation as pi by 32 d to the power 4. So this is the polar moment of inertia of a circular shaft, isn't it? And what will be the unit of this unit? If dia has a unit of meter, then the unit of this will be meter to the power 4. And if dia has a unit of millimeter, then you will get the unit of polar moment of inertia as millimeter to the power 4. So this is the polar moment of inertia of a circular shaft, pi by 32 d to the power 4. Next is polar moment of inertia of a hollow shaft. Suppose we have hollow circular shaft of a hollow circular shaft, right? So suppose we have a circular shaft like this. Circular shaft, this is a circular shaft, and this is hollow in between, so that there is some material here and some material here, and inside it is hollow, right? So like this is a hollow circular shaft, right? And the material is in this part only. So this is the part where the material is there, right? And suppose this is a circular, so dia, inside dia is given, say small d, and all outside dia is also given, say capital D. So outer dia of this shaft is capital D, and inner dia is small d, and this is hollow. If I make it here, you will get this. From when we see from side, you will get this vision, hollow circular shaft, right? Like this, and material is in between this part only. Right? This is the hollow circular shaft, right? And by definition, we know that the J is given by J, the polar moment of inertia, is the integration of r square dA. R square dA. When we solve it, we will get J will be equal to Ixx plus Iyy, right? This is our basic equation from which we can start, right? And this is the definition. By definition, polar moment of inertia is given by r square dA, right? So what is the moment of inertia of a hollow shaft in any direction, say x direction, in the plane of the circular shaft, this plane, right? And we have to find out polar moment of inertia about this axis, z axis, right? Polar moment of inertia is always in the perpendicular of this circular shaft, and in this plane there is x axis and y axis, right? So what is Ixx? That will be equal to pi by 64 d to the power 4 minus d to the power 4. Go to the basics where you have derived the moment of inertia of a hollow shaft, simple moment of inertia of a hollow shaft, not polar, simple moment of inertia of hollow shaft. Go to your basics, and Iyy, that will be equal to again pi by 64 d to the power 4 minus d to the power 4, outer dia minus inner dia, right? So what is xx here? This is our xx, and this axis is yy in the plane of this circle, right? And z is j or z is in the perpendicular to this plane, right? So j will be equal to Ixx plus Iyy. So this will be equal to pi by 64 d to the power 4 minus d to the power 4 plus pi by 64 again capital D power 4 minus small t to the power 4, and j will, you will get, when you solve it, you will get again the same type of equation, pi by 32 capital D to the power 4 minus inner dia to the power 4. So this is the polar moment of inertia of a hollow shaft, right? So we have find out the two polar moment of inertias, one for solid shaft and one for hollow shaft. You have to remember both.